But we'll talk about those at the end of class because they're relatively straightforward techniques. But I'm just glad that somebody found that because I have never done anything that was that big. So I'm happy to know that there's a limit to what it can do. So the next things we're going to talk about are, I'm going to go ahead and make a copy of this because we're going to make a copy of your sample data sheet because we're going to need them. Actually, yeah, we will. We're going to first create a regression. So we make a copy of this, let's put it at the end of our data sheets. And we're going to create just two regressions to compare. Do we know exactly what they are? Nope, we're going to just make them up right now and then go from there. Well, I'm going to delete this graph off of this one because we're not going to need it. And we're going to, actually, we'll do two models. We'll do one where we keep, so looking at our VIF summary, let's do one where we keep all 5, and let's do one where we eliminate the X1 data. Since it is linear, it is collinear with X4. So we'll do those two models, and then we'll compare them. So we're going to do a regression analysis. So we're going to data analyze. Eventually load. Oh, no, this is the wrong way. That's a different. Data analysis. We're going to go to regression. And we're going to choose our Y, obviously being our Y value. We're going to choose our X as being all the X's. So, like that. Tell it you have labels. Constant 0, no, because we want to have it regress our intercept. Give it an accurate counter. I always like to do residuals, residual plots, all that, because it just makes me feel better. And then we're going to put it in a new worksheet, and we're going to call this regression, and I'm going to call it all. So we're keeping all the data in there. So we run the regression, we get this. Let's take a look at our plots, our residual plots. If we haven't done that yet, our X5 looks good, looks pretty noisy, X4 looks good, X3, X2, and X1 all look. So it looks like our regression fits based on the data we provided, right? Okay, now he has earned the right to give all 3 of you. This is just, I like the game, the back and forth, and this is entertaining, but he has now the upper hand. All 3 showed up. Right?
Oh yeah. Oh, I've always said that.
Oh, I like the confidence. So we're going to look at this and we're going to say, okay, here are our coefficients for our system, and we're going to copy these over. I'm just going to copy these over to the other page so I can see them as we're doing this. I need the intercept too.
To the VIF summary page?
What's that?
You're copying it to the VIF?
I'm coming to where we made the copy of the sample data for our regression. I'm going to put it over there so I can build my regression. Because I don't have to flip back and forth between pages, so I'm just being lazy. Okay. So this is our Y, I would say for model all. This way I have it labeled in a way that's, I can identify quickly what it is. And we're going to put in the equation for that. So, using these coefficients, it's going to be Y equals, actually, because I don't have to deal with this, I'm going to get even lazier. So this is my Y, these are my coefficients for model all. I'm just going to label this so that I don't have to, this way I don't have to type the numbers all in, I can just reference them. So it's going to be the coefficient for X1 times the value for X1. And we're going to lock this coefficient term because we don't want it to move as we copy it down. And remember, this is a linear regression, right? This is a multilinear regression. So it's just adding the linear behavior of each one of these. Do you understand that? Like y'all get that? That this is all this is doing is a linear fit to all, the Y is linearly fit to all the X's. So then we're gonna do the coefficient for x2, we're gonna lock that, and we're gonna multiply it by the value for x2. And we're gonna do the same thing for x3. Lock it, times the value for x3. We're going to do the coefficient for x4, times, oh, let me lock that before I move on, times the value for x4, and then plus coefficient for x5, times, see if I forgot to lock it again, so lock it, times value for x5. Remember, you're not locking the x values, you're just locking the coefficients. And then plus our intercept, which we're gonna lock also. And we got 106 for that first data point, it's supposed to be 115, that's not bad. And then we're gonna copy it down. And just for curiosity's sake, let's look. 106, 95, 108, 119. So it's not a great fit, but it's not horrible from the looks of it. If we want to, we can even look, we'll plot it against y in a minute to see how it behaves. But now we're going to do the model where we remove one of our data sets. And we're going to remove the x1 data set from our regression.
Can you show the equation again?
Oh yeah, absolutely. It's just the coefficient times the value for each one. So this is the coefficient for x1 times the value of x1. Coefficient of x2, value of x2, and add those together. So you're basically creating a bunch of linear values and then adding them together, throwing your intercept on the end and calling it a day.
Is there like a shortcut to lock a variable?
F4. If you are on the variable, hit F4, it'll cycle through all the lock options. It'll lock both, lock, I think, column, lock row, and then unlock. Yeah, it's definitely much easier. That shortcut will save you a lot of headache when you're doing this. I'm gonna close this.
And then you added the intercept.
Yeah, just the intercept, yep, because that's just a standalone value, that's our offset function. Everybody get this? Everyone comfortable, you want to hold, or do you want to wait a second, or are you ready to move forward?
Regression? Yeah, what's it?
Okay, I'm gonna, because there was no one saying, hold on, we're gonna go ahead and move forward to the next one. So now we're gonna regress it, but we're gonna regress it based on our VIF results. And our VIF results said x1 and x4, they're pretty linearly correlated. They're not like over 10 where we'd immediately eliminate one, but they're high enough that we go, there's some possibility there, we should consider getting rid of one. And when we plotted them against each other in our, over here in this data, sample data, when we plotted them against each other, that's a pretty strong correlation, right? That looks, if I threw that up there and said, is there a linear figure? You'd say, yeah, those things are definitely directly affecting each other. So we can see that, so we're gonna eliminate our x1 data and regress it down. So we're gonna go back over to that sheet. Let me put it over here, just go out like that. But let me rename this as regression data. That way, yeah, we can. Okay, so now we're going to go, why do I keep coming out like this? Data, data analysis, regression, and our y is gonna stay the same. Everything's the same except our x's. Our x's are now only gonna contain x2 to x5. Because we've seen from the VIF data that x1 and x4 are functionally, this can be treated as almost like the same data set. And so we want to eliminate that. We want to regress and see how it behaves without it. We're gonna call this a new workbook, or sorry, a new sheet, and we're gonna go this regression, let's say without
When you press the first
x1.
one, please.
And just to make sure, you
Yeah.
said that you're doing, your y is.
My y is still my y,
Okay.
but instead of doing x1 through x5, I'm doing x2 through x5 as my independent variables, as my x range. Now, do y'all understand why I'm dropping x1?
I'll read them out to you
Because
later.
we're.
Yeah, we saw the VIF and we said there's a correlation, a collinearity there. One of these we have to get rid of in reality. Like, now, remember, our collinearity rules are, when you're doing VIF analysis, is if it's more than 10, strongly collinear, definitely get rid of it. If it's 5 to 10, there's a high probability of collinearity. So you wanna maybe dig into them more, and one of the ways I like to dig into it is just plot them against each other when I have two that are related like that, and go, yeah, it's there.
Yeah, I didn't
Um,
know this, so, zero.
Really, if I can get rid of it, once it's above 5, I will, because it's really a strong link. Especially when you look at the other ones, it was, you had a 5, like a 6.9, a 7, and then everything else was like 1.0 something. It tells you, yeah, there's too much of a linearity there, so we're gonna get rid of one of them. Okay, so we're gonna regress that, it's gonna spit out the results. If we look at these, X5 looks good, X4 looks good, X3 looks good, X2 looks good, so there's nothing here that gives me pause to say the data we threw out is causing a problem. I'm gonna copy these again because I don't wanna have to go back and forth. Go back up here, scroll over, gonna paste. So this is gonna be my coefficient for model without X1. This way I label everything and I can keep track of what I do a lot of labeling of my data because I don't wanna forget what stuff is. So I just encourage it when you're dealing with that. I just realized that, why did I not keep that in? Maybe it didn't like the slash, I bet it didn't. So I'm gonna say regression without, or WO X1. Probably just didn't like the slash in the name. So let me grab these coefficients again. Go back to the data, I'm gonna paste that there. And now I'm going to do the same type of equation again. So this is y without, y model without xy. And then just build it the same way again. So equals coefficient of x2, because remember we don't have an x1 in this one, lock it, and times the data for x2. So I forgot to actually put the times. Here we go. Lock it times the data for x2 plus the coefficient for x3 times the data for x3. Forgot to lock it, so I'll do it now. There we go. Plus coefficient for x4, lock it times the data for x4 plus the coefficient for x5. Oops, wrong one. X5, lock it, times the data for x5. Then add your intercept. And lock it. Now, if you'll notice, if you look at these coefficients, the x2 coefficient really didn't change much, right? Went from negative 1.05 to negative 1.04, or 1.06 to 1.04. That's about a 2% change, that's not much. Your x3 went from 0.440 to 0.443. That's less than a 1% change. Your coefficient for x5, it almost doubled. But notice your x4 became 1.94. It became drastically different because now it's having to compensate for the fact that whatever x1 change was introducing is now being functionally captured in x4. Because we're saying, because we know that those two are highly related. And so that's why we see them change the way they did. So we're gonna copy that down. But if you look at these values, they look very similar as you move your way down this list. There's really not a whole lot of difference. And if we want to see what that looks like, we could insert an XY scatter. That is a terrible plot. We're going to select the data. We're going to remove everything that's in here because I don't like it. We're going to add in data series, which is Y. Actually, we're going to add in Y model and Y model all. Our X we're going to use as just our Y data, so that we can see. Basically, we're going to compare the model Y to the actual Ys. So we're going to use the actual Ys as our Y data, and our model Ys as our Y axis data, just to see how they map. So then our Y is, this one's going to be Y model all, so that's this. we're gonna add y model without x1. X value again is our y data. Y value, model, that model, so the y minus x, the y minus x1 model. Let's see how it looks.
You said our X values was what again?
What's that? For this plot, x is our actual y data. So let me put some labels on the axis so you can see. Axis titles. So this down here is y actual, and over here is y model. We'll put a heading on this just to chart title, and this is model versus actual y. Or say y predicted versus y actual, let's call that y predicted versus y actual. And if I look at this, let's put a 45-degree line in through this, because this is what we would expect to have. So I'm going to create my data for a 45-degree line. So, actually, how do I make a 45-degree line on this graph? First thing I want to do is I want to make sure my axes are the same. So I want to go from let's say 160 to 160. That way my y and x look the same. That way I have the line I can draw like that. And then what I'm going to do is just create the data for my 45 line. And it's just going to be values along there. And I only really need 2 data points if I want to do a perfect 45-degree line. I can do the 2 corners. It'll work perfectly. So I'm going to put 0 and 160 because that's the high end. And then I'm going to go to this. Let's say chart design. Select data, I'm going to add a 45 line. My x is 0 to 160. My y is also the 0 to 160. You can see these green dots here, and then I'm just going to say, give me a line that's solid. Let's make it a dashed line. And let's change the color to not blue because it matches our other one. So let's make it, I have to do the line one. Give me a green to match with that. Why are you not turning it green? My marker is green. Yes, ma'am.
Can you help me direct this real quick?
Yeah, so what do you want to indicate?
So just to make sure, you said that the series is gonna be.
This is your x, and then for your all is this one, because it's the y model all.
So series name is one.
Right, and it's this data for your y value. Oh, no, that's the name.
Oh,
Yeah. So that's the y model all, what you have it. X should be this, your actual y. Data. This one, because this is, you're looking at y model all, not y without x1. And you do the same thing for y without x1. This is your x, this is your y. So if I look at this, if my data fits perfectly, it should follow that 45-degree line. If it fits well, it should follow that 45-degree line. Does it follow the 45-degree line? Yes, ma'am.
Why are we doing 45-degree line?
Because for a 45-degree line, it means that the 2 y's are equal to each other. And so the closer it is to that 45-degree line, the closer it follows your data being equal. That's why. It's basically y equals y. out of 45. So if y, think about it, it means y equals x, and what we've done is we've created one x, which is our actual data, or we've created one value as our actual data, one's our predicted, and if they fit perfectly, then you're gonna go y equals x line. And we do, I mean, it's noisy data, because it's not, none of it follows the line perfectly, but the fact is they're close to the line. And that's what we wanna see, is we wanna see that they fall close to that line, and they do. And both models, if I look at this, seem to predict it well. There may be a little curvature here at the end, but it's not, I mean, it's only 4 data points. It's hard to say that there's true curvature there. That could just be North Star data. We don't have enough data at that end point to say, oh, that's curvature, there's something weird happening. We just don't have that. But I look at this and go, this is a good regression. But how do I know which one's better? Well, let me ask you this. From a simplicity perspective, which model's better? The second one, right? Why is the second one better?
There's less variables.
Yeah, you're using less data, you're using fewer X's, and you're getting what looks like a fit that's as good. So that's your first instinct is, hey, that's probably the one I want, but we need to verify that. And we're gonna verify that using 2 different techniques. And I'm gonna write these names out because they are, one of them you might have heard the word before. The other one, if you've heard it, I'll be very shocked. I mean, nothing against y'all, I've just never heard this word before I started doing this work. The ACAIC information criterion. Which is the AIC. And the second one is the Bayesian. And that's one you might have heard, because there's like Bayesian is a type of distribution in statistics, so you might have heard it before. Bayesian information criterion. Or the BIC. Now, these are just tools. There's nothing fancy about them. There's a massive derivation behind them that we don't care about. What we care about is what they do. And what they do is you use them to compare models. That's the only purpose they serve. So the AIC value, the equation is what? AIC equals N times the natural log of RSS over N plus 2K. And I'll explain all the variables in a minute because I'm going to write the BIC equation because it's very similar. The BIC, which is just a modification of this one, says N times the natural log of RSS over N, looks exactly the same with you here, plus K times the natural log of N. That's a natural log. It's hard to tell. There we go. The only difference is the second term. Here. So, N, number of observations. So basically, how many rows are in your data set? Your K, number of predictors. So how many independent variables do you have? Plus 1. Why plus 1? What other thing are we regressing besides the coefficients? We get all of our slopes and then one other thing in a regression. The intercept. Yeah, we have another variable we're regressing. So that's why that plus 1 keeps showing up there, because when we regress it, we're actually regressing in, so the number of slopes, plus that intercept. So that's why we have that plus 1 term there in the predictors, because we actually have another predictor. We have the slopes and the intercept. Those are all predictors. And then finally, hopefully you remember this, at least RSS, sum of squared residuals. We've calculated this 1,000 times. You're going to be using it again. Now, what the thing you'll notice here is this is the only difference, that end piece. This is the penalty that it gets for predictors. The more predictors you have, the bigger the penalty you get. BIC penalizes predictors more than AIC does. So if your criteria, if your judgment criteria on your model is, I need to make it as simple as possible, which means get rid of as many predictors as I can, you're gonna use the BIC to compare. If you're not dealing with that as much, then AIC is perfectly fine. I personally, because this calculation is simple, just use BIC. There's no reason not to, and as a general rule of thumb, you always wanna make the simplest model you can. So, but just know that there are two criteria, both are perfectly valid. All you have to do is calculate it. Now the good news is, if we go to our regression sheets, we have all of our residuals already, right? So we can do, just on these sheets, the residuals squared. And we don't have to recreate all of our residuals again. We can make our lives easier. So we just take the residual, we square it, copy it down. Then because I'm lazy, I'm going to copy that column over to the other regression sheet and paste it, and it's going to fix the equation already for us so we don't have to type it all again. I'll give you a second to do those squared residuals. And so we're going to calculate the RSS, the AIC, and the BIC for all of these, for both models, and then make a decision on which one we think is the best, based on that. If we look at the adjusted R squareds, because we haven't done that yet, this one has an adjusted R squared of 0.7352. This one has an adjusted R squared of 0.7582, or 7585. So not significantly different. I would have a hard time saying one model is better than the other just based on R squared. There's a difference of 0.2 between them. 0.02. That is a tiny difference in R squareds. So let's now look at the AICs and BICs. So we have the R, we have the sum squared of the residuals. So now let's go ahead and calculate what we need. We need an RSS. We need to know what our N is. We need to know what our K is. I'm going to make these left shifts. This drives me crazy. Is that all we need for this? Yeah. So RSS, just the sum of the squares of the residuals, right? Done this a bunch of times. Remember that equation? If you guys don't remember this equation, we've used it before, but just to refresh your memory, RSS equals the summation from I equals 1 to n of yi minus y predicted, or y hat. Y hat squared. Which is what it calculates, that's what the residual is. So that right here is your residual for each data point. So we already had that calculated on that table, so we're just squaring them and then adding them together. Okay? We're just, instead of us recalculating like we've done in the past, we're gonna use what Excel's providing it. Let's not waste our time reinventing the wheel. So your RSS is equal to the sum of that column. Our N, how many observations do we have? Well, we can look here. We have 100, right? It even says, it even labels it, observations. So you know you have 100 observations. So, how many predictors do we have for the regression model with all of them? 5, and then plus 1. We have 5 predictors, plus 1, so our K is 6. Yeah, so you were right on the number of predictors. And then we add the 1 for the intersect. So now, let's just go ahead and calculate AIC. AIC equation is N times the natural log of RSS divided by N plus 2 times K. and we get an AIC of 447. Now, is that a good value or a bad value? Doesn't tell us anything about that. The key with this is that it is a value that we can use for comparative purposes.
What was K?
K is the number of predictors plus 1. So predictors are, remember, your slopes. Basically, how many variables are you using as your x's? You have 5, and then you have 1 plus 1 for your slope, so there's 6. And the IC formula is that guy up there. Natural log, n times the natural log of RSS over n plus 2k. So that's what I did here. So I did, you can see I did n times the natural log of RSS over n plus 2 times k. And so now we'll do the BIC equation. And because we're reusing a lot of the same information, I'm just going to copy this formula and paste it down here, and then we'll fix it. So this first part's the same. The only thing that changes is this addition term. So this becomes plus k times the natural log of n. And I'm going to put that in parentheses to make sure it doesn't screw it up. Make sure it keeps them together. Yes. Go back to BIC? Yeah, absolutely. Yeah, so what I did here is I took G29, which is our n, times the natural log of RSS, which is G28, over G29, which is RSS divided by n, so it's from that equation up here. And then plus, and now I just altered that n piece. So that's n times the natural log, or sorry, k times the natural log of n. And that's your addition piece. Okay, so what do these values mean? Absolutely nothing as they are. Okay, that's an important piece of information, is doing this for a single model tells you nothing. You have to be able to do it for 2 models and compare the data, because it tells you which one's better. And so far, we haven't really identified which one's better, we've just identified what the values are for this one. Now, the good news is, we can just copy this and paste it in the same position over on the other one and get our results. So it's coming out of F28. Oh, it's gonna screw it up, sorry. No. May have to, we wanna check all these to make sure. Yep, that's what I thought it was gonna do. So we need to make sure that our R squared is actually pointing at the right thing. So I'm gonna actually just fix this. So we're gonna put that up to there, we're gonna come down here, get rid of this blank spot. There we go. So our RSS is now right. Observations is is 100. Is our K still 6?
No, it's 5.
It's 5. There you go. Exactly. So we do that, and we get an AIC of 455.92. Basically this. Now let's make sure these are pointing at the right values. They are. Cool. So now let's compare. 447.67, 455.92. AIC of this 5 model one is slightly better than the 4. BIC, even closer. So what we've learned is, from a comparative values, those AICs and BICs are almost identical between the two. Which one would you pick? If we did it purely off of AIC and BIC, we would say, well, this one's lower is better. Just so you guys know, AIC and BIC, lower is better. So we go, cool, we're gonna use the one that has the lower AIC and BIC. But when I'm looking at this and I'm going, yeah, it's lower, but it's like 1% lower. I'd probably use the simpler model in that case. But you're valid with either justification. It depends on what do you value most. Do you want the one that seems to be the best fit? Then that tells you use the full model. If you want the one that you go, I really value making it simpler, use the one that has less data. Because these are close enough that I wouldn't justify one or the other off of the AIC and BIC. But if I'd see like 400 and 200, now I feel like I have to use that. And we can actually, I would recommend going through this exercise. Go ahead and do this where you eliminate both 1 and 4, and then do a regression, and you're going to see a model that fits worse, and your AICs and BICs are going to be worse. Because it's like, this model now just doesn't fit. Your RSS gets enough bigger that your data looks bad. Your AIC and BICs don't fit anymore. AIC and BIC are purely comparative tools. Raw numbers tell you nothing. So if you calculate those for one model and you don't have a second model to compare to, you've calculated them, but you haven't done anything with them. Okay?
So you want your AIC and your BIC to be equal?
You want they want it to be equal to each other. You want them to be low, like the one that has the lower ones is the better model from their perspective. But what you're gonna notice is they're closer on the BIC because the BIC said, well, this model, it doesn't fit as well, but you have less data. You have 20% less data you're using. So I actually like you, not as good as the other one, but you're closer. You're closer than what AIC claims because it penalizes having extra variables more. You're gonna notice that also as N increases, this number increases. So again, not only is it the number of data sets, because that's gonna affect your K, but less data means a better AIC and BIC. So if you can get a good fitting model with less observations, it's actually gonna award that also. And that's something else you can play with. Cut your data in half and see whether you can get a good regression. And you cut your data in half and you still get a good regression, your AICs and BICs drop, you're like, this model actually is better than the one I did where I had more data because the fit was good enough. But what's gonna happen is at some point your RSSs are gonna get worse and worse and worse, and your model's gonna fall apart. So that's that key, is it's that balance between those. Yes, ma'am?
Why did we choose to get rid of X1?
We chose to get rid of X1 because of the VIF analysis we did last time. So remember we did the VIF,
Oh.
and we found that X1 and X4 had values of about 7, and we said that if it's above 5, there's a likely collinearity. If it's above 10, there's definitely a collinearity.
So either way, we could have gotten rid of X4 and kept X1?
Right.
Okay.
And that would be actually a good exercise. Get rid of X4, keep X1, see if your model's better with one of them versus the other. I chose X1 because it had the higher VIF. That's the only reason. But if you look, 0.702 versus 0.696, that's not really, statistically, I would not consider that a difference in this. Okay, so I want to give you some quick summary things to take away from these. So that you have them fresh in your mind. I recommend you have this spreadsheet built doing all these calculations. I would store this information in there because I think it's really useful. So we call this summary of statistics. For model. And you're going to hear the term goodness. What's the goodness of the model? Or the goodness of your data set? You're going to hear that phrase used a lot. So this is just things to keep in mind. So we talked about root mean squared error. Lower is better. So you can do root mean squared error analysis on these models and see which one's better. AIC. Lower is better. BIC. Lower is better. Because these are all measuring error and complexity of the model. They're all doing, so that's why lower is better. VIF. Less than 5, ideal. 5 to 7, or say 5 to 10. Possible collinearity. I think there may be 2 L's there, collinearity. And then greater than 10. I would say highly light, or say high probability of collinearity. And the way to think about that on the VIF If it's greater than 10, you gotta throw something out. Once it's above 10, something's gotta go. And it's likely the data set's with 10. Between 5 and 10, consider it. If you can come up with a model that's simpler, that still fits as well, and getting rid of one of them, or potentially both if you can't link them together, do it. And then below 5, you're fine. Like, don't even worry about it. So other things to keep in mind when you're doing this analysis. And then, okay, yeah, I forgot to include this one. Just so you have it, your QQ plot. Straight line equals good. Yeah, that means if you plot it versus the normal data and it's a straight line, great. If it's not, transform your y by natural log, exponential, square root, squaring, something, and try it again, dropping the endpoints, whatever it is, and then see if it's linear. So the idea is get it as linear as you can by transforming the y data. That's the goal there. Okay. Are y'all comfortable with this? And this sheet is a great example of the goal of this course. Is when you get out of here, I want you to have this Excel portfolio with all these techniques demonstrated in your arsenal. So when you get out in industry, you've got this. Like, you have to do data regression and go, wait a minute, I think I have something with that. And you go back to your Excel and you can thumb through and go, oh wait, this. And you now have that as a reference sheet to build whatever it is you need in industry. I don't expect you to necessarily remember how to do this in detail when you walk out, but I expect you to remember enough that you can go to your Excel sheet and remind yourself. That's the goal. Because I understand that this is stuff you've never seen before. You're not going to use it when you get out of here right away. That's the reality. But hopefully it will strike something in your memory that goes, oh yeah, we learned about this. I know how to, I can refresh myself on this topic. That's the goal. Which is in your project, because now what we're going to be doing a lot is your project. You're going to take your data and we're going to bring it to class. You're going to get with your group and start doing this type of critique and this type of analysis of it. So the first piece you're going to be doing next time is the VIF. You're going to be introducing dummy variables if you need it. You're doing your QQ plot. Now, somebody pointed out that regression will only take 16 independent variables. For a lot of you, that's not a problem, but for at least one group, I think there's 21 independent variables in your data set. What do? Well, I will just demonstrate this by taking the sample data. I'm just going to make a copy of this to just show you, like, you don't have to do this. But, well, I would say go ahead and do this because we're going to show you how you deal with it. We're going to create a data set that isn't useful, and that's fine. It's not going to be a functionally reasonable data set, but for demonstration purposes, it'll work. And hopefully this will catch up with itself. Okay. So what I'm going to do is I'm going to give myself 25 data sets because I want something more than 16.
So if we have less than 16, we don't need to worry about this?
You don't have to do this, but it's useful to know it. That is what I'll say. So there's 10, there's 15 independent variables, there's 20, there's 25. So we get this. So here we have 25. I'm going to relabel them so that we have labels that actually fit. So let me bring that over. So we have up to x25. Now here's what happens if we try to do regression on this. We go data analysis, regression, and I was told it should fail. I actually haven't tested it, so we're going to find out. Our A, that's our Y data, that's good. Our X is now going to be all of these. And notice, they're duplicates of each other. So it's going to find regression coefficients that are like garbage. It's going to say, well, that one's 0. Well, yeah, it should be because it's identical with this column. You only have to fit it in one of them. Let's look at this. We're going to create this, and this is regression with 25 independent variables. Up, out of range, cannot have more than 16 columns. So what do? Well, there's a cool function. It's not as pretty as what you're gonna get out of this, and it doesn't give you all the information that you get from review regression analysis, but there's an equation called LINEST, linear estimator. It's going to do what the regression analysis does and return some of the same data, but it does it just all in this sheet. So this is why it might be something interesting for you to do if you don't want to go through regression. You can actually build this in there and play with it easy. So first thing it says now, hey, what's your known Y's? Well, our known Y's are, and do not choose a header. You can't tell if there are headers, so only choose the data. So that's our Y. It's okay, what are your known X's? Well, it's all of this. And I can select all of them. Constants. Do I want to set my intercept equal to 0? No. So I want to say true, I want it to be calculated. And it says, okay, return additional regression statistics? Yeah, return them all. Let's just go ahead and have it return everything it does. And so then it creates a table over here. All these NAs are supposed to be there. They're blank. There is no data provided in those. So NAs are normal in those. What it gives you is this information. And these are, and I'm going to label these so you can have them. This is, make sure that I'm doing this right.
So
Make
you
sure.
just put 0 for the constant?
It has 0 for some of the constants, and we're going to talk about that in actually a second. I want to make sure that it has them in the right order. That's why I'm checking it. Yep. What it's doing is this. M1, M2, M3. Let me drag this across. All the way up to M25 and the intercept. That's what this top row is. There's all the M's. And actually, let me just create a map of the table above it so you know what they are. Because I can't label the row below it. So let me do that. Control X. Let's move this up too. So that first row is in. Those are your coefficients. So this is the coefficient for x1, which is this one here. Coefficient of x2, coefficient of x3, and it just does that all the way across to coefficient.
Wait, is the first one the coefficient for y?
The first one is the coefficient for x1. X1. Yeah. And let me move this whole thing up so that we have it closer to the top and we can see what this represents. I want to put it by our data so we can see it. There we go. Now what you're going to notice is if I click anywhere in this, other than this top left, I can't edit it because this is a table created by the LINEST function. So there's no individual calculation in each of these blocks. This is all being done by the LINEST or LINEST function. Linear estimator or line estimator, depending on how you want to say it, so LINEST or LINEST. So that means that our slopes for these are zeros up until you get to M20. And then it's 0.8685. Then it goes through like that. You're going to see the normal things here. Actually, this may be bottom by one. Yeah, and then there's a gap. I don't know why there's a gap there. We go back and look at our all regression. It fits these exactly. Right? It's actually following that perfectly. 0.8686, 105, 0.44, and we go over here and we see 8686, 36644, and then negative 1.05. So it's actually shifted. That's weird. I have to look at my data. I may have applied it. But what it's doing is it's giving you the regression of those. So it's basically showing you what each of those are. The second row of this is the standard error of each of these coefficients. So I'm gonna say slope, standard error. And so it just does the same thing, which is a lot of the same data you already were getting from the regression analysis. The difference is it's just providing it in a tabular format, SE of the intercept. Then you're gonna get some other statistical information. That is your R squared. So that 0.7707 is your R squared. Now you're getting to things that the next one you probably aren't as familiar with. Oh, and then this 9.101, that's the standard error of your Y. Then you have also your F statistic. We haven't talked about that. We don't have to worry about it. You have, that 94 is your degrees of freedom in your data. Like, it's actually giving you a ton of statistical data in this one table. And then finally, you have, and this is gonna get where we're gonna have some confusing, this is your sort of sum squared of your regression, your SS, which is also known as your SSR. And the other one is your, what we've seen 1,000 times, RSS, that thing over there. SSR and RSS are different variables. Just so you guys know, that's SSR. So RSS we already had over here previously, but I want to remind you what it is, and I'm going to show you the difference between those. Okay, we've had 3-letter acronym for residual stuff multiple times. We had RSS, which is the summation of I equals 1 to n of yi minus yi hat, so yi minus y model squared. We've seen that 100 times. We now have SSR, which is summation. That's not a good summation. Summation of I equals 1 to n of, I can remember this one. This one is, I wrote it down because it's one we don't use as much. Yi hat, so the model minus the average of your actual Y data. And so what this is saying is, how much of my variation in my data, especially it's a measure of how much of the variation in your data does your model predict accurately? Like, how much is my Y changing in my in the actual data versus, so off of the normal, off of the mean, and how well is my model predicted? It's a measure of that. It's not a perfect measure, it's a representation of it. This is functionally error, right? This is what the Y should be versus what I calculated to be. So this is unpredicted variation. So what my model's not catching, because it's your residual, is the difference between, so it's like, hey, model says it should be this, and it's actually this, and this is the difference between them, and this is where it's screwing up. This is predicted variation. And if I add these together, I get the total variation of the model, which is actually something you've calculated before, SST, which is the summation of I equals 1 to n of, let me try to get this right, yi minus y bar squared. And this is actually technically the sum of these two. And we've used SST and we've used, we used TSS, not SST, this is TSS. We've used TSS and RSS, but we haven't used SSR yet. And these two added together will give you this. If you expand out these summations, you'll find out like you end up deleting or subtracting the summation of yi's or yi hats from there, and you're left with the y and y bars. So that's why it actually works out that way. But my point is, you can use Linus or Linus to get your slopes or your coefficients for, I think, up to 64. It'll handle. So if you can't do the regression, you can always do Linus to get your coefficients. If you don't want to do that, you can do what is called a piecewise analysis. So instead of, let's say you have 21. You have this, how much time do you have? 4 minutes, perfect. This is perfect for this. Everyone have this? Cool. If you want to take a picture of it real quick, go ahead, and then I'll erase it. Am I out of your way? Yeah. Okay. I can't suck in the rest of these. Okay, so let's say I've got a data set that has like x1, x2, x3, x4, up to x21, because that's the one, the example I was dealing with. You can do a piecewise analysis of this, and what I recommend is if you can do 16, you do up to 16. So I do my my VIF for x1 to x16, and I get my result. Then I go, I'm gonna also do VIF. So 16, I'm adding 5 more, so let's take 5 off the end. So I'm gonna do x6 to x21, and do my VIF. You'll notice I'm getting n separate, but I'm not getting coverage. Now I'm going to take 8 from each end. Then I'm going to do my VIF for x1 to x8 and x21 minus 8. I think it's going to be 13 to 21. That may be right. X13 to x21. This allows me to get coverage across all of them and comparing them all in some combination. Then if I notice any VIF values that are elevated, they don't have to be like all the way up at like 5 or 6, but if like all my values are like 1, 1.03, and then I have something that's like a 2 or a 3, where it looks like it's an outlier, I'm gonna record all those. So now I'm gonna record all that are larger than rest. And what I mean by that is this is you look at it and go, that seems large compared to the other data sets. If it's 1.05 and 1.13, those are all still low. But if you get something that's like 2, 3, and other rest are sitting around 1 or 2, or 1 or lower, or sorry, like 1.5 or lower, those are the ones that are gonna stand out. And I do that for all of these. And I'm likely not gonna get 16. I'm only gonna get like 3 or 4. Now I do a VIF of those together because they're the ones that are actually likely mapping each other. If I map those in VIF and I don't get that correlation between them that's bigger than 5, keep them all. If I get some that are higher, okay, I can't keep them. If you do this and you're like, they're all relatively independent that I'm not as comfortable with Linus and I want to use regression after I've done this, you can, what I would recommend is then choose 5 to remove based on what you found here as the ones that were the most collinear. They may not be collinear at all, but that's the reality of it. Sometimes you may want to just drop data. But you can also do Linus and just have it. Once you have that, you can do that. Yeah.
Why are you going from 60 to
Because I'm basically getting the 16 at this end and the 16 at this end. Because I have 5 extra ones. I can't do more than 16.
So it's supposed to be 16.
No. I want to overlap. I want to get 16 data points.
Oh.
Yeah, so I'm making, and I want coverage. I want to have overlap in my data set. That's why I did this last one where I overlap at the ends, so that everything gets covered at least twice. That's the goal there. So I'm doing as many, and you can keep doing combinations of data and do more mapping like that, but generally this will give you enough to get that. And then once I do that, I can make my decision on, if it turns out they're all non-collinear, I'd recommend using Linus then, get your coefficients from that, and do that instead of using the regression tool. Because it's giving you the same information, right? The only thing it's not calculating is your adjusted R-squared, but you can calculate an adjusted R-squared if you want to. And just let it run from that, okay? Everyone comfortable with this? Okay, so we're gonna start looking at your data, because now you're gonna do VIF, and you're gonna do, dummy variables if you need them, and you're going to do, the QQ plot for your data for your project. By let's do what, Wednesday for class, I think? So Monday, we're gonna talk about if you find you have a ton of data and it's a pain to work with and you don't really have a good, like, we're gonna talk about how do I decide what variables to get rid of if this doesn't eliminate any. Like, let's say I have 35 variables and I go through this and it's like, they're all like 2 or below. There's no good reason to throw anything out, other than my tool can't handle more than 16, not the best answer. So, and you would never say that to your boss. Well, my tool can't handle more than 16, so I'm not gonna do it. You would never say that. So we're gonna show you techniques on how to decide what to get rid of if you want a simplistic model. And this is where we're gonna talk about primary principal component analysis. So what we're gonna do is, this is where we're gonna go over eigenvalues and eigenvectors, getting comfortable with that stuff, and how it points you towards the direction of your data you wanna go. What it's gonna do is say, hey, it turns out this is the direction your Y changes the most, and that is affected by these 5 variables only. These other ones really don't have an influence. So you go, okay, and how much does that tell me? Well, it tells me 40% of my change in Y. Cool, I need more. Okay, well, it turns out these 4 will give you another 30%. And like, it basically allows you to identify new axes in your data by combining variables, and now you go from having 31 variables or 50 variables down to like 10, when all said and done. And now you can actually regress it and use the tools you have. Okay? Yes, ma'am.